So as Fred said, I'm Ivana Tanasova from VMware's open source program office. I'm a contributor to the project. And I'd like to share with you about our service mesh interface integration and how this inspired us to improve our traffic observability. We all know that service meshes are a hype topic at the moment. These are just some of the available implementations, and more continue to appear, like, for example, Kuma and Mesh are some of the latest I've heard for, and the latest that appeared on the landscape. And each of those service meshes was separately developed following its own concepts. And unlike Kubernetes, which became the standard for containers orchestration instead of one of many solutions, most service meshes develop very well on their own way. And we cannot point at one and say this is the standard for service mesh. And all of this makes switching between service meshes quite hard. And if you don't want to be binded to a specific implementation, or if you want to build unified solutions on top of that. And having so many implementations caused a need for common specification that would unify the different service mesh APIs. SMI, the service mesh interface, has been around for less than a year, and so far its goal is to provide a common portable set of service mesh APIs. So for benefits like that you can create applications that use service meshes without binding to any specific implementation, and that you can easily switch between different service meshes. The service mesh interface covers some of the most common service mesh API use cases, like traffic policy, which is for applying policies for identity and transport encryption across services, like traffic telemetry, which is for capturing key metrics like latency and error rate between services, and like traffic management, which is for shifting traffic between different services. What SMI consists of, it's specified as a collection of customer source definitions. These are the types of specs that are available. Traffic specs defines how traffic looks on per protocol basis. It consists of these two customer source definitions, and these resources work according to the available policies to manage traffic at a protocol level. Traffic access control is for configuring access to specific pods and routes based on identity of a client. And traffic metrics expose common metrics for use by different tools like dashboards and autoscalers. And traffic split is for allows users to incrementally direct amount of traffic. And this can serve ingress controllers and service mesh sidecars and so on. And these are the customer source definitions that are available. As we saw, service mesh interface, CRDs support the upper level protocols that the other service meshes, the traditional service meshes implement, while the network service mesh covers layers 2 and 3 from the OSI model. And why we decided to integrate with them, we've heard about this service mesh interface on a keynote announcement during KubeCon Europe this year. And we found it's a great idea to unify our API with the other service meshes. There were two reasons for that. We wanted to be considered as a service mesh as the others, and having strongly different API could somehow serve as a separation in the future. And the second, having the same API makes it very easy to combine network service mesh with some upper layer service mesh. So we started looking for similarities between us and the SMI spec. And the first thing we focused on were the traffic metrics spec. And we realized we can apply that to observe traffic. And we also realized that having networking without metrics and observability is comparable to having not having logs for your containers. It's very hard to observe what's going on if something wrong goes on. And we observed what's how their specification looks like and how they present metrics. You can see that this is a traffic metric YML configuration file. They present metrics by names. For example, they have response latency, failure, XSX count, and different amounts of metrics that serve for that. And how our metrics looked like by that moment. All we had were big blocks of data in the cross-connect monitor that were provided by the forwarding planes. Initially, those metrics weren't even logged there. And the VPP and kernel forwarding planes were sending metrics about the traffic that's going on. But those metrics weren't triggered anywhere nor observable. And just imagine searching through thousands of lines of logs to find the specific connection you're working on, and then starting to investigate to see all the records that happened for that connection, because this is sent on every update event. So you need to find all those events and then start analyzing and start collecting those data on your own. And we can agree this is not very convenient. So this is how we started our work to make that traffic metrics more observable. And this resulted in some very good benefits for the project. First, we fixed an issue we had with the forwarding planes about not sending metrics. And we couldn't notice about that because, as we said, those weren't tracked anywhere. Another benefit, what we had by that moment is information about the client and an endpoint in a cross-connect data, was the network namespace. And we can agree that this is not something anyone would identify their service with. You could hardly investigate specific connection, as you shouldn't really know between which client and endpoint this connection is when you look at your logs. So change we did was exposing some more human readable data in the cross-connect monitor. We exposed the pod names of clients and endpoints together with the namespace to have a unique representation of a client and an endpoint. And the third benefit, we saw that the Service Mesh Interface API was collecting metrics data from Prometheus, and that one of the requirements to integrate with them is to store our metrics in Prometheus. And another requirement was the format of the metrics. What we had, the forwarding planes were sending metrics like RX bytes and TX bytes, RX packets and TX packets and error packets. And we decided that we can apply those, as previously shared, the traffic metrics configuration YML for SMI. We decided to apply the data that our forwarding planes were sending as metric names in that configuration, and the units to be the exchanged byte and packets accordingly. So what we had finally is we are now collecting that data in Prometheus, and so this is tracked for every connection, every update event, and you can search, you can specify if easy to see from those data. You can specify your client and endpoint, and you can see what traffic happened there. And what's the takeaway? What started for us as an integration effort turned out to be much more beneficial for the project than expected. Because out of the benefit of the integration itself, everything that was required from us to do by reaching there was worth on its own. And it was very beneficial for the project. So that I want to say thank you. And if you have any questions.